Okay, these are the lectures for the Module 5, Compilation, Lexing and Parsing. We're going to talk for compilation for about 3 weeks. We'll do Lexing and Parsing this week. We'll talk about semantic analysis next week, and we'll talk about program optimizations the week after that. These are the outcomes, and as usual, just go back at the end of the module, convince yourself that you have these, that you understand these. So why study compilation? Some universities will offer an entire course on compilation, and others don't. At Embry-Riddle, we do not have an entire course on compilation, but you do talk about it in this class. The argument against is that you will almost certainly never design a compiler for a brand new programming language. Even if you do, there are software tools out there that will help you and hide the details of the process from you. But there are also arguments for. First of all, basic understanding of the compilation process really is helpful for software engineers or anyone who's developing code. You need to understand that the program you write is not the program that gets executed. The program that you write will get ripped apart by the compiler, it will get rearranged, and so the end result is going to have the same input-output behavior that you wrote, but it's going to actually be a different program. Also, some of your code design decisions may be affected by compiler behaviors, or understanding that there are certain tools that you can turn on and off in a compiler. You may want to know what those are so that you can have the compiler target your specific code appropriately. Threaded, multi-threaded applications are becoming far more common than they used to be, and they can introduce race conditions if you don't understand how they work. So if you think that when you produce a line of code, that line of code gets performed atomically, that's incorrect. The compiler may only perform a third of that line of code, and then, the processor may only execute a third of that line of code. And then the processor goes to somebody else, and then when it comes back, the data that you had actually could be modified, could be changed. Knowing where these threats are can be helpful to understanding how to avoid race conditions and even security issues. Also, the same design techniques, the same principles that we use for compilers to parse programs are the same techniques we use for parsing data. And you probably will have to parse some data somewhere in your academic or your professional career. And so it is helpful to understand how that works. The overview of compilation, and again, different authors will list these steps differently, and the reason is they might want to emphasize different portions of the compilation process in their text. But basically, it goes through with lexical analysis, which is determining the role that the different tokens or the different strings in your program play, and then syntactical analysis, which is also called parsing, which is quite frankly just determining if you've written a legal programming statement and a legal program. And then semantic analysis, which is talking more about the behavior of the program. The primary semantic analysis, or the most obvious ones, are things like type checking. Do the types match up in a particular statement? Following that, once the compiler believes that you have a legal correct program and all of the types play together so the semantic analysis plays out, then the compiler will perform optimizations on your program, the goal being to manipulate the code sequences in such a way as to either reduce computational cycles or reduce the amount of memory that you're using at any point in time. Finally, the compiler will get down to code generation, and by code generation we mean the machine code generation. Remember, every chip that is sold in the world is designed to have a hardwired set of commands that it can accept and perform. And these are all in machine code, 10, 10, 10. And different sequences of zeros and ones will trigger certain actions inside the chip. So your code has to be reduced to these very small, finite steps of execution. And then lastly, assembly. Assembly means that usually your large program is developed in bits, the code is generated in bits and pieces, and then in assembly they're basically linking all the bits together. In fact, sometimes this is called linking. Some authors will lump code generation and assembly together, and it's kind of a fuzzy line where those two part. The idea behind assembly, though, is basically the machine has to understand where in memory to go find other segments of your code. So that's what the linking or assembly is about. We're going to focus in this module on the lexical and syntactical analysis. Next week we'll talk about semantic analysis. Okay, lexical analysis. This is often called lexing. Every string in a program we're going to refer to as a token. Now, that's kind of a fuzzy term in the sense that what is a string? Well, your whole program is a string. On the other hand, any individual line of code in your program is a string. On the other hand, a single variable is a string. Basically, anything that's separated by white space is a string. The equal sign is a string. The equal sign is a string. So the word string there is a little bit fuzzy, but let's treat it as any sequence of symbols then that is separated by white space. That sequence of symbols we're going to call a token. And so the compiler takes in your program token by token, and then the role of lexing is to determine what role does this token play in this statement. Is this a variable? Is this a mathematical operation? Is this a function call? What is this thing? So the job here is to replace the tokens in your program with just the lexical equivalent. So for some examples, if I say x equals 12, it just gets replaced with, for example, this is just an example, var assignment op number. Notice the details are gone. Only the roles are there. This could have been y equals 12 and it still would say var assignment op number. So what's happening is all of the details of your individual variable names disappear. The individual numeric values that you use disappear. And they all come down to just these simple rules of token, token, token. X equals 2 times y. Okay, that's a variable, an assignment operator, a number, a math operator, and another variable. By the way, a lot of people use identifier or ID instead of variable. I'm using var for variable. The beginning of a for loop looks like this. For I equals 0, I less than ni plus plus. Oh, that's a for. Oh, okay, that's a keyword for. And then the parentheses is part of the terminal, so that can stay. Then we have an assignment statement, a Boolean test, and another assignment statement. The assignment statements can be broken down further. You can think of this term assignment statement as a non-terminal in the grammar. And then that can be broken down further. Well, what is an assignment statement made up of? Oh, it's made of a var, an assignment operator, and some expression. Maybe a number, maybe something else. So that's what's happening in the lexical analysis. We're replacing the specific variable names with just, hey, this is what it is, it's a variable. We're replacing the specific math operators with just, this is what it is, it's a math operator. Why? Why do we do this? Well, because in order to do the parsing, we rely on the BNF grammars. All of the programming languages in the world are defined by their BNF grammars. And you cannot possibly create a BNF grammar that will cover all of the infinite variations of the variable names that people may come up with. So instead we just tokenize. Oh, that variable, I don't care what the name is. All of the basically infinite names that you can create for a variable all get reduced to one token, a var or an ID, identifier, or whatever's in the BNF grammar. All of the different math operations you can use all get reduced down to one. Here's an example. This is from the Java BNF that's on the link on this page. An assignment operator. We have equals, times equals, divide equals, percent equals as modulo. I think there's 12 of those things. All 12 of those get reduced just to assignment operator. Even with all of that reduction, Java has about 170 rules in its BNF grammar. And you can look at them here at this link. So that's what we're doing. All we're doing is pulling out the details and focusing on the structure of each program statement. Once that happens, we can ask the question, is this string in the language? And now we have a manageable BNF grammar. And again, a BNF grammar with 170 rules, we're going to call that manageable. Remember, your program is a string, a single statement is a string, a variable is a string. So basically, the question is this a string in the language, is usually asked at the statement level, and then a sequence of statements becomes a program. So we can use the BNF rules to see if the string can be parsed from the grammar. We've talked previously about how you can derive strings. If you start with the start symbol, can you derive this string? So one way to answer this question, is this string in the language, is the top-down method. You begin with the start symbol, and you use the BNF rules from left to right to produce the string. And the most common form of that is something called recursive descent parsing, which recursively calls parsing functions specific to various program forms. For example, let's say you see the for keyword. Then say, this is a for loop. I'm going to have to call my for loop recognizer. And so you go through the for loop, and inside that for loop is another for loop. You see the word for again. And you say, I'm going to have to recursively call my for loop recognizer again. And so that's why it's called recursive descent parsing. It's recursive because it calls itself over and over again. It's descent because it's going from the program level to the statement level down to the smaller statement level, down to the individual token level. This is not the most common form. Using the BNF rules from left to right is intuitively obvious. That's how we did it for derivation. This is not the most common form. Instead, what people will do is use the BNF rules from right to left. They use the bottom-up method. They start with the string and try to use the rules backwards to produce the start symbol. A more common method is to use the rules from right to left. Start with the string and try to produce the start symbol. If you can start with the string and use the BNF rules backwards and produce the start symbol, the string must be in the language. Remember, these rules are reversible. So why would that be a common way to do this? The reason is it reduces the options that the compiler can take at any point in time. If we look at this example grammar over here, I've got C, non-terminal C, can be replaced by ACB or AB or D. So I've got three options. If I see a C in my string, I've got three options here. Well, let's do it backwards. If I have ACB, I really only have one option, rule 2. And if I have a D, I only have one option, rule 4. Unfortunately, I've produced an unfortunate grammar here where there's two options for AB. We wouldn't have that, and I'll talk about that later. But the idea here is you're reducing the options. If I have a C, it must be that I'm going to reduce that to an S. If I have a terminal A, I'm going to reduce that to a non-terminal A. A terminal B gets reduced to a non-terminal B. And so what are you doing? You're reducing the number of options the compiler has at any time, and in fact the goal is to reduce it to 1. Unfortunately, my grammar doesn't do that here, but we'll talk about that in the next lecture.